Hey, welcome to The Explainer. So today, we're going to dive into a pretty huge shift that's happening in the world of statistics. It's all about moving away from a simple yes or no answer towards something way more nuanced. How strong is the evidence? So let me ask you a question. Have you ever found yourself trying to explain what p less than 0.05 actually means and just ended up tying yourself in knots? Yeah, if you've ever felt that the classic p-value is kind of confusing or maybe just doesn't tell the whole story, trust me, you are not alone. Okay, so let's get right into it. We're going to start with the problem with p-values. For decades, they've been the absolute gold standard in research. But more and more, people are starting to question if they really deserve to be on that throne. So what is a p-value, really? At its core, it's the answer to a very, very specific question. It tells you the probability of seeing the data you saw, assuming your initial idea, the null hypothesis, is true. In other words, it just tells you how surprising your result is if you assume there was no effect to begin with. It's not, and this is the key part, the probability that your hypothesis is actually true. And this is where the big limitations start to show up. A p-value only ever looks at the null hypothesis. It completely ignores how well the data might fit your actual idea, the alternative hypothesis. It just gives you this binary reject or fail to reject decision. It's kind of like a smoke alarm. It screams at you when something's up, but it has no idea if you just burned some toast or if the whole kitchen's on fire. It just gives a yes-no warning. So, if p-values are giving us this really incomplete picture, what's the alternative? Well, this is where a totally different way of thinking comes into play. A philosophy that really reframes how we should think about evidence itself. You see, this boils down to a huge philosophical split in statistics. On one side, you've got frequentist statistics. That's where p-values live. They see probability as how often something happens over the long haul. But then there's this other camp, Bayesian statistics. And for them, probability is all about a degree of belief, a confidence level that we can and should update as we get new data. And the star player in the Bayesian world is something called the Bayes factor. Now, instead of just looking at that one null hypothesis, the Bayes factor does something way more intuitive. It directly compares two competing stories and answers a really simple question. Which idea do the data support more, and by how much?
All right, enough with the theory. Let's make this super concrete with a real-world research example and see how these two different approaches really stack up against each other.
Okay, so picture this. A study with 65 people. Researchers are looking at the connection between how anxious someone is about math and how well they do on a test. The null hypothesis, H0, is that there's absolutely no connection. The alternative, H1, is that there is some kind of connection, and the data they found shows a sample correlation of 0.37. So a p-value might just tell you it's significant, but what does the Bayesian analysis tell us? Well, it spits out this number, 13.93. And this number, this is the real key to understanding the evidence. So what does that 13.93 actually mean? In plain English, it means the data we found are almost 14 times more likely if there is a real connection between anxiety and performance than if there isn't one. See how clear that is? It's a direct, intuitive statement about the strength of the evidence. And we can even put a label on that strength. There are these common guidelines, called Jeffrey's guidelines, that help us interpret these numbers. A Bayes factor between 1 and 3 is kind of anecdotal evidence. 3 to 10 is considered moderate. But where we landed, around 14, that's considered strong evidence. It's not just black or white, significant or not, it's a spectrum. Now, I know what you might be thinking. This all sounds pretty complex, maybe a little intimidating mathematically, but here's the best part. Modern tools have made this whole process incredibly, incredibly easy. And you wouldn't be wrong to think that. For a long, long time, this was a huge hurdle. Doing a Bayesian analysis meant you pretty much needed to be a coding wizard with a deep, deep background in statistics. But that's just not the world we live in anymore. Seriously, free, open-source software like JASP has totally changed the game. It gives you this simple point-and-click interface that puts all of this power right at your fingertips. I mean, just look at how simple this workflow is. For that math anxiety study we were just talking about, you literally just pop in the summary stats, n equals 65, r equals 0.37. You pick a prior, which is just your starting assumption, and JASP has a great default one, and boom, instantly you get the Bayes factor and all these cool plots. It really is that straightforward. And the results you get are so intuitive. Take this chart for example. JASP can actually visualize how your beliefs should change.
So let's say we started out thinking both hypotheses were equally likely, like a 50-50 shot. Well, after seeing the data, our belief that there is a real correlation jumps all the way up to 93%.
And here's another awesome thing you get, something called a credible interval. What this tells us is that we can be 95% confident that the true real-world correlation is somewhere between about 0.13 and 0.55. And unlike those old-school confidence intervals, this is a direct, intuitive statement about probability that you can actually explain to someone without tying your brain in a knot. So, what does this all mean? Where is all of this heading? Well, this new approach, this Bayesian way of thinking, is really starting to shape the future of how we do research.
Okay, so let's boil it all down. What are the big things to remember here? First, Bayesian analysis gives you a continuous scale of evidence, not just a yes-no answer. Second, it lets you gather evidence for both sides of the coin, for your alternative idea and even for the null hypothesis, which is something p-values just can't do. And maybe most importantly, tools like JASP mean that anyone, and I mean anyone, can use these powerful methods.
At the end of the day, this entire shift comes down to changing the one fundamental question we ask of our data. What if, instead of just asking, is there an effect, yes or no, we started asking a better question: how much evidence is there for an effect? That single shift in perspective, well, that's the heart of the Bayesian revolution, and it promises a future where our science is so much more informative, transparent, and just plain better.